Welcome everyone, and thank you for joining us today. I'm excited to present to you an introduction to cylindrical cells. This is the first slide of our series, and it sets the stage for understanding why these batteries are so important. We'll explore their key features, applications, and benefits. So, let's dive in and discover what makes cylindrical cells a popular choice in the world of rechargeable batteries. Let's take a look at how cylindrical cell naming works. It's primarily based on two key measurements, diameter and height. For example, when you see a cell labeled 18,650, that means it has an 18 diameter and a 65 height. Similarly, a 21,700 cell has a 21 diameter and a 70 height. These numbers are very helpful in quickly understanding the size of the cell. There are several common cell types you'll come across, like 10,440, 14,500, 18,650, 21,700, and larger ones like 26,650, 32,700, and even 4680. Each of these has its own typical dimensions and applications. Now, why do these standard sizes matter? Well, first, they make compatibility and replacement much easier. If you know the standard size, you can quickly find a compatible cell without much hassle. Second, they help speed up pack design and facilitate automation during manufacturing. And finally, using standard sizes ensures more uniform assembly and better quality control, which is crucial for reliable performance. So, understanding these naming conventions and standard sizes really forms the foundation for designing and working with cylindrical cells effectively. Today, I want to talk about the different chemistries used in cylindrical cells, which are chosen based on specific application needs. First up is LFP, or lithium iron phosphate. It has a nominal voltage of about 3.2 volts. One of the biggest advantages of LFP is its high safety profile and thermal stability, making it a reliable choice for many applications. It also offers a long cycle life, typically between 2,000 and 6,000 cycles, which means it can be charged and discharged many times without significant degradation. You'll often find LFP used in energy storage systems and solar storage solutions because of these qualities. Next, let's look at NMC, or nickel manganese cobalt. It has a slightly higher nominal voltage, around 3.6 to 3.7 volts. This chemistry is known for its high energy density, which is crucial for applications where space and weight are limited. The cycle life is moderate, generally between 500 and 1,500 cycles, but it balances that with the ability to deliver more energy in a smaller package. That's why NMC cells are commonly found in electric vehicles and portable devices, where size and weight are critical factors. To sum up, LFP offers safety and longevity, making it ideal for stationary storage, while NMC provides higher energy density and a more compact size, perfect for mobile applications. Understanding these differences helps us choose the right chemistry to match the specific needs of each application, tying back into the overall theme of optimizing battery performance based on usage requirements. Now, let's take a closer look at some example specifications for a typical lithium iron phosphate, or LFP, battery cell, like the one with the code LFP 32140. This cell has a nominal voltage of 3.2 volts, a capacity of 15 amp hours, and is capable of delivering at least 3,000 charge-discharge cycles. Its internal resistance is rated at or below 12 milliohms, which is important because lower resistance translates to better efficiency and less heat generation during operation. When we talk about performance parameters, we're looking at a few key things. First, the internal resistance, which impacts how much energy is lost inside the cell. Next is cycle life, or how many times the battery can be charged and discharged before its capacity drops below a usable level. Then, maximum discharge current, often expressed as a C rate. This tells us how quickly we can draw power from the battery without damaging it. And finally, the operating temperature range, which is vital because batteries have optimal temperature zones for safety and longevity. Before assembling a pack, it's crucial to verify these important specifications. Electrical parameters include the nominal voltage, which, as I mentioned, can be 3.2 V or sometimes 3.7 V, depending on the chemistry and design. Capacity, typically expressed in amp-hours or milliamp-hours, indicates how much energy the battery can store. Energy rating, measured in watt-hours, gives a complete picture of the total energy capacity. Charge cutoff voltage and discharge cutoff voltage are critical because they define safe operating limits to prevent overcharging or overdischarging, which could damage the cells or reduce lifespan. In summary, understanding and verifying these specifications ensures we select the right cells for our applications and build reliable, efficient battery packs that meet our performance needs. Let's talk about what makes a good cell. A good cell has no dents, no chemical leakages, and the dimensions are correct. It also shows good IR and OCV readings, which should align with the data sheets provided for each cell. Before we move into manufacturing, it's essential to inspect cylindrical cells thoroughly for safety and quality. This way, we ensure only the best cells make it through the process. The inspection checks include a visual inspection for dents, rust, or leaks, and a dimensional inspection to verify height and diameter. We also verify the weight to ensure consistency, and electrical testing for open circuit voltage and internal resistance. Now, these inspections are crucial because the applications of these cells are quite diverse. They are used in electric vehicles, energy storage systems, solar battery banks, power tools, laptops, and even UPS and backup systems. Remember, only cells that pass all these checks and are approved should move forward to module assembly. This process guarantees that the final products are safe, reliable, and perform as expected. Inspection and proper application are key to the success of cylindrical cell usage in various high-demand scenarios. Now let's move on to the key aspects of visual inspection. First, when we look at chemical leakage from a cell, there are certain signs to watch for. You might notice brown or yellow stains on the surface, which indicate leakage. The surface may feel sticky, and there could be signs of corrosion around the cell. Additionally, an electrolyte smell is a strong indicator that the cell is leaking. The risks associated with such a cell are significant. A failing cell can overheat or even vent, leading to potential hazards. The corrosive electrolyte can pose health and safety risks, so it's crucial to handle these with care. The correct action in this case is to strictly reject the cell. Store it in a sealed tray to contain any leakage, and dispose of it following the guidelines specified in the MSDS. This ensures safety for everyone involved. Next, let's talk about cells that are dented or deformed. Identification here includes noticing dents on the body or cap of the cell, deformation, or an uneven shape. These physical damages are serious because they can compromise the internal components. The main risk is that such damage might cause the separator inside the cell to break. This can lead to an internal short circuit, which in turn could cause thermal runaway, a dangerous situation where the cell overheats uncontrollably. When you see a dented or deformed cell, the action is clear. Reject it immediately. Mark it as fail and move it to quarantine. This prevents any potential safety issues down the line. Remember, any cells showing signs of chemical leakage or physical damage should never be used or stored with good cells. Bad cells must be identified and rejected promptly to maintain overall safety and reliability in our operations. All right, now let's take a look at what happens after the cell inspection process. When cells pass all the necessary tests, these include physical inspections, internal resistance checks, open circuit voltage measurements, and capacity grading. They are considered good to go. These are the cells that meet all our quality standards and are ready for the next stage, which is module assembly. You'll notice that these cells are marked with a green box color code. This color is crucial because it signals that these cells are safe and ready for production. Green is universally recognized as a sign of safety and go-ahead, so it helps streamline the process on the manufacturing floor. Additionally, each of these cells is labeled with a clear tag that says, PASSED/ready for assembly. Along with this label, we include the batch number and the date, which helps with traceability and quality control down the line. Overall, this step is vital because it ensures only the best, fully tested cells move forward in the manufacturing process, maintaining our high standards and ensuring the reliability of the final product. Now, let's talk about quarantine cells. These are designated areas for cells that have borderline or ambiguous test results, or sometimes slight capacity mismatches. They also serve as a holding place for cells that need to be retested after a stabilization period. The purpose here is to ensure we carefully monitor these cells before making any final decisions. You'll notice the color coding is yellow or orange, which signals caution or that a review is pending. It's a visual cue that these cells require closer attention. The labeling on these cells states "quarantine awaiting retest," and you'll find specific reasons for the hold noted on a tag attached to each. This helps us keep everything organized and transparent, making sure everyone on the team understands why these cells are in quarantine and what actions are needed next. Overall, quarantine cells are a crucial part of our process. They help us ensure accuracy, safety, and quality control before final results are confirmed. Now let's talk about rejected cells, which we also refer to as fail cells. These are the batteries or cells that didn't pass our inspection process. For example, if a cell has physical damage like dents, scratches, or even leaks, it gets flagged as a fail. We also look at the electrical performance. If there are abnormal IR or voltage drops, those are clear indicators of issues. Additionally, if a cell completely fails the capacity grading test, it's marked as rejected. To make sure these cells are clearly identified and separated from the good ones, we use a red box color code. Red signals danger and is a visual cue that these cells are not safe or suitable for use. And to avoid any accidental use, we label these clearly as rejected or scrap. This labeling is crucial because it ensures these cells are fully isolated from the rest of the production line and won't cause any problems down the road. Overall, this step is vital for maintaining safety and quality control. Rejecting cells that don't meet our standards helps us ensure that only reliable, high-quality batteries make it into the final product.